Hello, everyone. It's a pleasure to be here. I would like to give an overview of a line of research that several people, including myself, did on trying to understand the complexity of a fundamental big data problem. And this is a joint work with Artur's batch course and Ludwig Schmidt, my students, who did all the work. All right, so my day job is an algorithm designer. Right? I design efficient algorithms for a variety of problems, and from the algorithm designer perspective, we are living in a very interesting times. Okay, because on the one hand, the amount of data that is being produced grows pretty quickly, right? So that we have seen this in the previous talk, and this also explains why there are so many initiatives, data centers, right, data science centers, and so on. So this means that the input to our problems is growing. But at the same time, the processing power, at least for the general perspective computation, is not necessarily improving, right? Transistors have been shrinking for a while, but this trend recently hit the wall. And of course, Moore's law has been announced to be dead several times, but this time, it really seems like it's dead. At least according to a panel at a recent ACM conference. Okay, so this is a very interesting combination of trends because the input size is growing, right? I mean, pretty quickly, but our processing power does not, right? So this leads to some very interesting confluences, right? Which are perhaps best summarized by this very nice tweet, right? I will read it. An engineer from Google told me today that he had a hard time finding available machines for production because of the NIPS deadline. Okay, so this is something that many people in the audience can sympathize with, right? All I can say that if Google cannot do it, we are all in trouble. Okay. So what can be done? Well, of course, there are lots of things that are being already done, right? For starters, you can focus not on the general purpose hardware, but on specialized hardware. So, right? So we have TPUs, GPUs, which are tuned in to particular applications and can solve problems much faster. Now, as I mentioned, my day job is an algorithm designer, right? So there is lots of opportunities for that, right? Designing faster algorithms, which are randomized, approximate. There is lots of modern techniques which help solve the problems faster. But today, I would like to focus on the dual question, right? On trying to understand what are the limits of further algorithmic improvements, right? So what are the boundaries below which we cannot push our algorithms any further? And there are at least two reasons for doing it. I mean, one is science, right? It's a fundamental question. I mean, it's a scientific inquiry, right? Like, what are the limits of what we can do? But there is also a pragmatic aspect, right? Which is if you know the limitations, it can actually help you design better methods, right? Because the life of an algorithm designer, as a metaphor, looks like this, right? There is only so much time. Right, but there are many avenues to explore, right? Many problems, many variants of the problems, and so on. And because of that, since you don't know what can be solved, what can, there's lots of effort being wasted. Right, so if we had some guidelines, like some pose that tells us, okay, here you hit the limit, but here, you don't. This simplifies the design process considerably. Okay. So, of course, this is not a new question. I mean, people have been studied limitations of computation for a long time, right? And perhaps the best known formulation of this is captured by the famous P not equal to NP hypothesis, right? Which states that there are problems called the NP-complete, which cannot be solved in a sub-exponential time, and all of them are equivalent to each other. Right, so this leads to very fundamental methodology for showing that some problems cannot be solved, essentially by blaming it on others. Right, so okay, I cannot solve this problem, but my problem is equivalent to all these other problems, right? So it's not my fault. Okay, and this has been an extremely successful approach, but there are certain limitations to that. And in the context of big data, perhaps the main limitation is the fact that it defines the notion of efficient as a polynomial time, right? Now, of course, in many situations, it makes sense, right? And square and cube and to the 4 algorithms are often very efficient. However, once your data is big, it might be no longer true, right? So for example, if you have a quadratic time algorithm, if you start to run it on gigabyte of data, it might take years or maybe even hundreds of years to finish. And of course, maybe you can solve your problem over a gigabyte, but then you can move on to terabyte or even more, right? And very quickly, you are going to hit the wall. So, one approach to this problem is to be more conservative in terms of what we mean by efficient, right? So, for example, we can focus on a near-linear time or linear time, right? And there are several approaches to that. But if we do it, then we hit another problem, which is that the P not equal to P conjecture by itself does not really distinguish, right, between different powers, right? So n square, n cube, and to the 100, they are all polynomials, right? So just by the conjecture as stated, we cannot really distinguish between these very different complexities. So in order to fix it, we need two things. First, we need stronger conjectures, right, which are stronger than P not equal to NP, which help us get stronger conclusions. And also, we need better ways of transferring hardness for one problem to another, right? We cannot just solve that problems are equivalent up to some polynomial. We have to have some quantitative way of connecting different problems. So this has been a very active area of research over the last few years, and there are several conjectures that have been postulated, which helps us develop this kind of a theory. In this talk today, I will focus on the strong exponential time hypothesis, which is one of the more popular ones. So this hypothesis postulates complexity of the well-known satisfiability problem. Right, so in satisfiability problem, you are given a formula, right, which is the end of ORs, and the goal is to determine whether there is a way to assign true or false values to the variables in order to make this formula satisfiable. Okay. Now, the strong exponential time hypothesis postulates that this problem cannot be solved in time, which is slightly better than 2 to the n. Okay? So notice that the problem has a trivial 2 to the n solution, right? You can just enumerate all the assignments, right? So this is a very, very sharp conjecture, right? And furthermore, it's a significant strengthening of the P not equal to NP, which only assumes that satisfiability cannot be solved in polynomial time, right? So this conjecture really raises the hardness threshold from polynomial to anywhere below 2 to the n. Okay, and it's a very strong conjecture, and because of that, it's sometimes referred to as a P not equal to P on steroids. Right, it's a much more powerful conjecture, which help us get much stronger results. All right, so once we are armed with this hypothesis, what can we do? So in the next few slides, I will give you a few examples of limitations that one can prove using this assumption. All right, so the first problem that we focus on is the well-known edit distance problem, right? You are given 2 sequences, and the goal is to figure out what's the minimum number of insertion, deletions, of substitutions that are needed to transform x into y, okay? So this is one example, okay? If you have some word like kofifi, okay, and you want to see what it means, right? You can take your pick and compute the edit distance between this and this, right? Which happens to be 4. Because if you perform these 4 operations, you can transform kofifi into coverage, okay? So this is one application, right? I guess to Twitter understanding, but really the main warehouse is computational biology, right? Because edit distance and generalization alignments, right? I mean, these are things that computational biologists are solving every day. All right. So what is known about this problem? Well, it has been studied for a long time, and the first algorithm for exactly this formulation is due to Wagner-Fischer. They came up with a very elegant quadratic time solution. Okay, but then the problem has been studied for the next few decades, and essentially for the general problem, for the general case, the only improvement is logarithmic, right? So people have been working hard on it, but this is again, for the general case, this is the only improvement we got. Now, there are, of course, much better algorithms for various special cases, right? There are better approximate algorithms, bounded distance algorithms, like for special inputs. But again, for the particular case of, for this general case, this is the best thing that we know, okay? So this was a kind of a mystery, and in a very recent work, we shed some light on this mystery by showing that, in fact, there is no quadratic time or subquadratic time algorithm for this problem unless the strong exponential time hypothesis fails, right? So this gives an evidence that this quadratic dependence is in fact tight. It's not a proof, right? Because for all we know, a set might fail, right? I mean, but it gives a certain limitation, certain barrier to further improvements to these important problems. All right, so this is first example. I think that people are, organizers are pretty serious about time. So I will skip the second example, okay? It deals with the batch backpropagation in neural networks. And the bottom line is that, again, we get the bad news here, right? If you want to solve the batch gradient computation over a network of size m, over m examples, the n times m is, again, the best thing that you can do unless the set fails, right? And in fact, similar lower bounds can be proven for kernel SVMs, kernel regression methods, and a few other things. All right, so continuing with the theme of bad news, here is another example, right? So kernel density evaluation. I mean, it's a very natural problem with many applications. The basic idea is that you have a certain density, which is a mixture of a few of some distributions, like mixture of Gaussians, for example. And you want to evaluate this density in a bunch of places. Okay, so more formally, these are kernels, right? Gaussians or polynomial, and so on. And you are given endpoints, which now define the density function, right? It's a mixture of a bunch of basic distributions, and you want to evaluate this in endpoints, okay? So, so what can be said about this problem? I mean, it has many applications in machine learning and statistics and so on. What can be said about the complexity? I mean, this problem can be solved very efficiently in quadratic time, right? Well, it can be solved very simply in quadratic time, right? Because, I mean, it just follows from the definition, right? I mean, you have n sums to compute. Each sum has n terms. Okay. Now, in low dimensions, there are much faster algorithms for this problem, right? So in particular, the well-known fast multiple method solves this problem in nearly linear time in low dimensions. But unfortunately, once you get to higher dimensions, n squared time is pretty much the best thing you can do in the worst case, right? Again, you can do Monte Carlo random sampling, which in certain situations run faster. But again, if you have arbitrary inputs, n squared is the best running time now. So, consistently with the previous theme, we managed to show that there are some bad news on this problem. Namely, for a Gaussian kernel, there is no subquadratic time algorithm for this problem, again, under the same assumption, okay? So that seems like a sequence of bad news. However, in this particular case, there is actually a silver lining, right? Because this result holds for a Gaussian kernel. However, for a polynomial kernel, we're actually able to show that there is a nearly linear time algorithm, right, which has a multiplicative approximation ratio, where the approximation ratio is arbitrarily close to 1. Okay, and I should mention that the way we arrived at this algorithm is essentially by eliminating other possibilities, right? We proved that for Gaussian kernels we cannot do it. Then we start to think what other kernels are out there so that we can prove the hardness for. We did not succeed to prove hardness for polynomial kernels, and then we switched sides and managed to prove that the algorithm actually exists. Right, so this illustrates the power of limitations. Once you can establish limitations, you cut out certain avenues which help you focus your effort on problems that actually have some hope to succeed. All right, so there's some good news, so it's a good time to wrap the talk. So to conclude, I gave you an overview of current state of the art in trying to show quantitative limitations to our basic big data problems, right? At the distance, neural networks, kernel methods, and so on, right? And this is a very growing field with lots of results being published frequently. Now, there are lots of and we have seen that there are lots of bad news, but we also have seen that negative can lead to positive, right? Which are, having the limitations can help us understand the complexity much better. Now, there are many fascinating questions, and in this audience, I would like to focus on one of them, which is the worst case versus average case, right? So far, all these lower bounds, all these limitations I described hold for worst case scenarios, right? Where we want algorithms to work for arbitrary inputs, right? But of course, many of these problems are statistical in nature, right? So inputs, they are random, they are sampled from some distribution, right? So it's not really that clear what worst case limitations really tell you about the complexity of this problem. Right? So it's a fascinating question, and there is some work in this direction, but there's probably more questions than answers. So I don't have answers here, but we have a plan, right? So this is a good time for advertisement. Okay, so a bunch of us here at MIT, from IDSS, CSAIL, Math Department, and so on, formed a group called MIFODS, MIT Institute for Foundation of Data Science, which is very interdisciplinary, right? It includes people who do mathematics, statistics, and theoretical computer science. And the goal of the institute is to study exactly questions like that, right? Which span several different fields, for example, statistics and theoretical computer science. And we have a bunch of programs, one program per semester. And in particular, spring 2020 is devoted to statistical and computational trade-offs, right? Which is exactly, the type of questions related to this problem, okay? So, I don't have answers, but, hopefully in the SDSCon number 4, right? Hopefully we'll, for the first time, have some answers. All right, so that's it. Thank you.
So we have time for several questions.
Thank you. I'm very encouraged that you're going to look at the statistical component of the problem solving. Does that include dynamically, as you perform the computation, building estimates of your error bounds or error approximations, closeness to the final solution?
Are you asking from the limitations perspective or the upper bounds?
I'm talking in terms of the algorithm, not merely computing the answer,
right?
But the algorithm as it's computing,
right?
Determining its estimate of what error it has in the current position or level it's computing.
I see. Well, it can be done because the algorithm I mentioned is based on a particular form of importance sampling. Right, which means that as you get more and more samples, you can actually narrow the confidence intervals. Right, the way we describe this algorithm is okay, you give me confidence intervals. I will tell you how much this algorithm has to run, but you are very much right that you can actually compute this confidence intervals on the fly. Yeah, that's a good point.
In the center here, I have the mic. May I? So can you say, like in a sentence, what the reductions look like? That really, I'm really asking, are you defining a class of set complete, if you will? Reductions go both ways.
Right.
And if they're like linear reductions necessarily, on the backprop problem, if you have one-bit numbers, if you're doing XOR NIST, if your data are 1 bit,
yes.
Does it matter? They used to have the same results, or if you make approximate results, can you get a better speed up, better lower bound for your backprop example?
Sure. So let me start from your second question. I should emphasize that our limitation is for the batch version of backprop, right? So we are given m examples. You have a network of size n, and we can show that essentially running backprop m times is optimal, right? Now, to get this answer, this limitation holds even if you want to know the gradient approximately, right? I mean, the details depend on the activation function, right? But that's roughly the overall, the gist of the result. And the result is not very sensitive to particular configurations, right? Now, again, this is lower bound in the worst case, right? So we cannot show that for MNIST data in particular, this lower bound holds, right? All we can show is that there is no algorithm which always runs on any data set runs in, say, subquadratic time. And the first question.
Just sketching out how the reductions work. So if you've created a class
Sure,
of
sure,
completeness.
yes, yeah, right. So currently the reductions go as usual through a sequence of reductions, right? So there's a prior work which establishes connection between the satisfiability and some other quadratic time problems. So what we do is take those quadratic time problems, which is actually very natural, right? Like closest pair in high dimensions, right? And we reduce those problems to, say, edit distance or the kernel methods and so on, right? Now, the state of the art right now is that the reduction go one way, right? So this is in contrast to NP completeness, right, where all these things are equivalent, right? We don't have it here, and this is actually another major open question, right? To be more precise, there are islands of equivalences. So for a collection of problems, you can show the equivalent, but these results in particular, the reduction only goes one way, right? So you don't really have this strength in numbers evidence, right?
So I understand that your quadratic lower bound essentially says there's no economy of scale if I want to compute endpoints for my density estimator. How about if I wanted to is that because you actually need to reduce from closest pair, or but if I wanted to prove that there's no sublinear to compute for 1 point, is that something that would be trivial or that would be much harder?
I see. So you are asking what happens for the problem where not for the batch version, but just for a single point, right? I think that this would need to be formulated appropriately, right? Because I mean, if your input is of size n, well, there is an upper bound of n and the lower bound of n as well, right? So in a way, from this perspective, the bound is tight. But I'm guessing that you could probably formulate this problem as a data structure, and then I'm sure if I understood your question.
Well, I mean, just rather than giving you endpoints, I'm telling you compute at 1 point, right? And now so the obvious one takes linear time. I have to compute the evaluation for each of my k of x minus xi.
Correct.
And I give you only x.
Right.
So now the size of the input is n.
Right.
And I'm asking, is there a sublinear? Is it hard? I mean, is it trivial or much harder to prove that there's no sublinear time algorithm to actually
if there is no sublinear time algorithm. Okay. Yes. So it's relatively straightforward to prove a sublinear lower bound. Okay. Yeah. Now, again, it could depend on, what's your approximation, right? Because, of course, you can randomly sample. It gives you some guarantees, right? But for the multiplicative approximation, it's relatively simple to solve, to show that, yeah.
Okay, I think we are out of time for questions, so you can catch Piotr during the break that will come. But before that, Elizabeth has some announcement to make. And we thank Piotr again for the talk.